Next, let us consider a more general case of multi-server queues with finite waiting space. Okay, so the arrival and the service times is basically the same with MM1K. It's just that this model have a multiple server. Okay, so the approach here is identical to MMC. Okay, except that the arrival rate lambda I must now be 0 whenever your I or your state is greater equals K. So there are no arrival because you have a finite waiting space. Okay. So here for MMCK, basically for the arrival rate, okay, lambda I, we will have, okay, so the first range for your lambda I, okay, you will have two range for lambda I separated here, okay. So the value would be lambda, okay, for your I equals to 1 until K minus 1, and the value will be 0 when your I is greater equals K. And as for the service rate, mu I, okay, so you will have three range here. Okay, the first one is when your state is less than C, okay, from 0 until C minus 1 here, okay. The second range would be when your state is between C until K. And finally, when your state is greater than K. Okay, so for your service rate mu I, you will have I mu, okay, when your I is equals to 1 up until C minus 1. And then it will become C mu, okay, when your state, okay, is equals to C up until K. And it will be 0 when your I is greater than K. Okay, so by using our prior theory developed in MMC, so you will have your pi I equals to lambda to the power of I over I factorial times mu to the power of I times pi naught, okay, for your I equals to 1 up until C minus 1. And then you will have lambda to the power of I over C to the power of I minus C times C factorial times mu to the power of I pi naught, okay, for your I equals to C up until K and 0 otherwise, okay, or I greater than K. Okay, so basically the value of your pi naught here, okay, so by using the knowledge that we've learned previously, okay, so for the value of pi naught, you will have 1 over summation of I equals to 0 until C minus 1 lambda to the power of I over I factorial times mu to the power of I plus the summation of I equals to C until K lambda to the power of I over C to the power of I minus C times C factorial mu to the power of I. Okay, or you can just write the bottom part, okay, to the power of -1, okay, which will basically gives you the same value. Okay, so next, in order for us to simplify, let us denote R equals to lambda over mu, which gives us rho equals to R over C, or equivalently lambda over C mu. Okay, so we're going to consider the second summation here. We're going to simplify this term. Okay, so the summation of I equals to C until K for lambda to the power of I over C to the power of I minus C times C factorial mu I. Okay, so you're going to rewrite it, and then we will get R to the power of I over C to the power of I minus c times c factorial, okay, by taking out r to the power of c over c factorial. So you are left with r to the power of I minus c over c to the power of I minus c, okay, which will gives you r to the power of c over c factorial, okay, rho to the power of I minus c. Okay, so you're going to consider, okay, for two cases here, okay, which is rho not equals to 1 and rho equals to 1. Okay, so this summation here can be simplified to r to the power of c over c factorial times 1 minus rho to the power of k minus c plus 1 over 1 minus rho for the case of rho not equals to 1, and for rho equals to 1 you will get r to the power of c over c factorial k minus c plus 1. Okay, so therefore for your pi note you will basically have two values depending on your rho. Okay, so for your pi note you will have, okay, so the summation here, the second term we're going to bring forward in order for us not to get confused with the first term that still have the summation symbol. Okay, k minus c plus 1, okay, this is the power of rho over 1 minus rho. Okay, the bottom part r to the power of c factorial k minus c plus 1, okay, and then plus, okay, this term here again, okay, summation of I equals to 0 until c minus 1. Okay, simplify the term, we will have r to the power of I over I factorial. Okay, the same here, over I factorial. This is for the case of rho not equals to 1. This is for rho equals to 1. Next, we will determine the measure of effectiveness, okay, for MMCKQ. Okay, so we're going to start with LQ. Okay, so for MMCQ queuing model, we will only consider the measure for the case when rho is not equals to 1, because the derivation of the case where rho is equals to 1 requires the application of L'Hopital's rules twice, so we will not cover it in this course. Okay, so we will only consider the case where rho is not equals to 1. Okay, so we're going to start with LQ first. Okay, so for your LQ here, the summation of I equals to c until k I minus c by I, okay, which is basically the same for I equals to c plus 1 until k, so I minus c to times pi I, okay, because the first term when I is equals to c will get cancelled. Okay, so we're just going to consider for I equals to c plus 1. Okay, and then you can just write down, okay, the value of your pi I when your rho is not equals to 1. Okay, so you have lambda to the power of I over c I minus c times c factorial mu I by naught. Okay, so then we're going to factor out pi naught times r to the power of c over c factorial. Okay, so we are left with the summation of I equals to c plus 1 until k for I minus c r to the power of I minus c over c to the power of I minus c. Okay, r equals to lambda over mu. Okay, and then so copying back, we're going to further simplify the term. So you have I minus C, so this is rho to the power of I minus C. Okay, so next we're going to factor out one of the row. So we will have pi naught RC over C factorial rho. Okay, so I equals to C plus 1 K. So okay, so I minus C times rho to the power of I minus C minus 1. Okay, we can further simplify the terms. Okay, over C factorial times rho. Okay, starting from n equals to 1 until k minus c. So we sort of subtract c terms, okay, so that we will start from 1 and then up until k minus c. So we're left with n rho to the power of n minus 1. Okay, so next we will have, okay, so basically the summation term here. Okay, so we're going to use the derivative. Okay, so this is basically the derivative of the summation of n equals to 0 until k minus c for rho to the power of n. Okay, so then what we can do is we will determine the summation and then we're going to differentiate it. Okay, so pi naught times r to the power of c rho over c factorial. Okay, and the sum of the terms can be simplified as 1 minus rho to the power of k minus c plus 1 over 1 minus rho, and then you're going to differentiate this term. Okay, which will give us, okay, so LQ equals to pi naught times RC times rho over C factorial. Okay, so differentiating the terms, you will get 1 minus rho to the power of k minus c plus 1 minus 1 minus rho k minus c plus 1 times rho to the power of k minus c over 1 minus rho square. Okay, so this is the value for your LQ. Okay, or you can take, okay, 1 minus rho square to be put here. Okay, so that you will get sort of a simpler looking term, okay, in your bracket, but the value is just the same, k minus c. Okay, so that is your LQ. Okay, so next, in order for us to obtain our L from our LQ, so we're going to recall from MMCQ. Okay, so where our L is equals to LQ plus lambda over mu, but since this is the case of finite waiting space, we're going to consider the efficient arrival. So then we will have our L is equals to LQ plus lambda efficient over mu. Okay, so this is our L for rho not equals to 1 for MMCQ. Okay, so following that, we will have our W equals to L over lambda efficient and WQ equals to LQ over lambda efficient. Okay, so that wraps up for our measure of effectiveness for MMCKQ for the case of rho not equals to 1. Okay, so you have all four: LW, LQ, and WQ. So let us have a look at one example of MMCKQ. Okay, so we're going to consider an automobile inspection station. Okay, so it has 3 inspection stalls. Okay, so each with room for only 1 car. Okay, so it is reasonable to assume that the cars wait in such a way that when a stall becomes vacant, the car at the head of the line pulls up. Okay, so basically this tells you the queue is following the first in first out regime. Okay, so the station can accommodate at most 4 cars waiting at one time. So okay, so you have 3 cars in the inspection stall. Okay, and then it can accommodate further more 4 cars waiting. Okay, so the arrival pattern follows Poisson with mean of 1 car every minute during peak periods. Okay, the service time is exponential with mean 6 minutes. Okay, and then the chief inspector named John wished to know the average number of car in the system during peak periods and average waiting including service, and also the expected number per hour that cannot enter the station because of full capacity. Okay, so 3 things that John wants to know. Okay, so the first thing is number of system here, the second is average weight, and the third one is expected number that cannot enter. Okay, so first we're going to extract out all of the information. So you have 3 inspection stalls, okay, which refers to your C equals to 3. Okay, and then you have further 4 waiting space. Okay, so your K is equals to 3 plus 4. Okay, so equals to 7. So this is an MM37Q. Okay, so next we're going to determine our arrival rate and also service rate. Okay, so the arrival with mean of 1 car every minute, so we will have our lambda equals to 1 per minute. Okay, and then your service time, okay, so exponential with mean 6 minutes. Okay, so 1 over mu is 6 minutes, so you will have your mu equals to 1 over 6 per minute. Okay, so now that we have our lambda and mu, okay, so you can start to determine or help John, okay, to find what he wants to know. Okay, so first what you can do is you can also simplify the term, so you will have your r equals to lambda over mu, which will gives you your r equals to 6. Okay, and then your rho you will have r over c, which is 2. Okay, and then first what you have to determine is of course your pi naught. Okay, so your rho here, okay, is not equals to 1. Okay, so first please determine your pi naught. Okay, and then second, okay, so what you have to do, okay, after you have your pi naught, then only you can determine your measure of effectiveness or probability in being in state I. Okay, so question number 1, John wishes to know the average number in the system during the peak period. So what is it that John wants to know? Is it L or LQ or W or WQ? So average number in the systems refer to L. Okay, so number 1, you need to determine the L. Okay, number 2, okay, so the average weight including service. Okay, so we're talking about the time in system, okay, not waiting time. Average wait including service basically means the time in the system, waiting and receive the service. Okay, so number 2, you want to know your W. Okay, and then for question 3, okay, So the expected number per hour that cannot enter the station because of full capacity. So full capacity refers to the probability of the state being in full capacity, meaning state being in state 7. So first you have to determine your probability of the system being in state 7, and then how you're going to determine the number or average number of car that cannot enter the system is you're going to take the value of your pi 7, which also represents the fraction that did not manage to enter the system, and then you're going to times with your arrival rate. So that's how you get the average number of car that is not able to enter the system. So the value that you will get here is in per minute, because your unit is in minutes. So what you have to do is you have to times with 60 to get the average per hour. So that is for the example. We will discuss the solution or the answer to this example later during our live session. So that is all for this week. Thank you very much.